Hello again, everyone. After a long study on the energy in magnets, which is a very difficult subject, especially for professionals who lose their trust due to the fact that all the relevant videos I have seen so far are fake, I have finally come to the point where I can share the results. It is perfectly normal for most people who are interested in this abuse subject to be skeptical about what I am about to tell from the very beginning. However, when the experiment I will tell you is done by you, you will see that your doubts are unfounded. I tried to show with live footage videos as proof that we can gain a little extra magnetic energy from permanent magnets with our electric motor of a very different design, which we have been able to produce after more than 10 years of work for which I have previously applied for the patent. However, since it is very difficult to see the results in person and be sure of the results with access to the same motor and necessary measuring devices, I tried to present my proof again with this experiment, which can be done more easily with materials accessible to everyone, is based on the same principles and whose mechanism I designed. Experimental measurements lasting for months were made many times with different magnets and coil windings, and similar results were obtained. In the meantime, with the experience gained, an original mechanism with an additional mini coil winding and switches was prepared, and an effort was made to standardize it with a measurement method that could be easily done by anyone, and over time, especially the lost. It has been modified many times to include an auxiliary switch mechanism in speed measurement and has been brought to this final version, which provides easier and more accurate results. I prepared this video so that I can share the evidence of the experiment and its method of execution with the link whenever I want, through a common platform such as YouTube that everyone can access, and so that interested people can watch it and reach me. I tried to explain the experiment and the preparation of the experimental setup in as simple and detailed a way as possible. With this video, I aim to present evidence of the existence of magnetic energy, which some people call infinite or free energy from permanent magnets, which is actually not infinite but limited, and which is added to the system, even if a small amount, so that everyone can clearly see the results when they do it. It is also worth noting that although we can present evidence of a free extra magnetic energy obtained from magnets, we are still far from creating a self-rotating perpetual machine with today's permanent magnet powers. However, the result of our experiment proves that such a machine is not impossible if permanent magnets that are much stronger than today's ones, which can provide a large amount of magnetic energy without friction and other losses, can be discovered after technological developments, just like the electric motor whose measurement results I showed in previous videos. Now, through this experiment, we will try to see again whether additional magnetic energy is released by giving current only in periods of time to a mechanism that represents a movement similar to that of an electric motor, that is, with a permanent magnet on one side and a coil winding on the other side, just like the coil windings in an electric motor. Thus, by comparing the total amounts of energy consumed and gained within a certain period of time, we will be able to reach the same result more easily with a not difficult experiment carried out with materials accessible to everyone. Let me first try to summarize what we will do, so that it can be shaped in our minds without getting into the details. With the help of a switch, we will give current to a large coil winding for a short time. Meanwhile, the coil winding will start to attract the magnet, which can be wound like a pendulum at the end of the rope opposite it, and immediately after the magnet touches the coil winding, we will close the switch and cut off the current. We will measure the electrical energy we spent until the moment of contact and the energy lost due to heat in the mobile with the help of an oscilloscope that can calculate the energy consumed by the integral mathematical operation of the power waves that we will create by mathematical multiplication of current and voltage waves in the oscilloscope with separate mathematical operations. When the front contact surface of the magnet connected to the wire, which we fixed as a continuation of the wire coming from a different mini coil winding that we will place in the main coil strand, and the stretched conductive wire, which acts as a key placed 1 cm before the contact limit, touch each other and the direction change in the waves at the moment of contact, on the oscilloscope we will be able to see and calculate the speed of our magnet at the moment of last contact and the kinetic energy we obtained. Finally, we will be able to compare the total energy gained versus consumed and see whether there is any magnetic energy gained from the extra permanent magnet. Now let's move on to the details of the experiment. We created a very simple stand where we will place the materials. By tying it with a rope, we turn it into a balanced pendulum that can move back and forth easily, and then we hang the coil winding on top of it so that it centers on all sides. Thus, friction during movement will be close to zero. In order to be able to make easy comparisons and reduce the margin of error in control experiment measurements, we adjusted the coil winding amount to be 1 ohm, which is a resistance value that will not be too low, and to be the same as the shunt resistance value we will use. I fixed the coil winding 5 cm ahead of the pendulum. A powerful power source is required to deliver current to the coil winding. I used a 12-volt 9-amp battery. As it is known, those batteries can provide much higher current than the capacities written on them for short periods of time. A simple LED transformer or any power source can also be used instead of the battery. However, it is necessary to pay attention to the fact that they are far enough away from the coil winding during the experiment and other details that will prevent electrical noise. It is sufficient for the oscilloscope we will use to examine the waves to have 2 channels, especially in which the energy can be calculated by field measurement of the integral function on the power waves created over time by the mathematical multiplication process of the channels. I used an oscilloscope that the mathematical operation options are very affordable for this. When we start the experiment, we turn on the switch connected to the end of the extended cable and start the current. And then, we just need to turn off the switch, especially after the moment of contact, which will cause the shunt resistor to overheat. When we apply electricity to the coil winding, the following stages occur. First, it touches the stretched wire and then the coil winding. It compresses the coil winding backwards at a micro level. It cannot move forward anymore, and the permanent magnet remains stuck to the coil winding for a while. At these stages, after the peak waves that occur due to contact with the stretched wire, there is no observable change in the opposing force that occurs in the coil winding during contact for a very short time, and then the opposite labor does not occur. For this reason, while the current is still distributing, the waves formed no longer increase in the same direction, and the waves continue to run parallel for a very short time, during which there is no observable change in the back EMF. Then, it turns towards the opposite side of the side it was directed towards before. We can now see this point, the moment of contact, on the oscilloscope when the waves begins to increase in parallel in the same direction. On the line where the magnet touches the coil winding, 1 cm before the contact point, we stretch thick wire or similar material, which does not contain iron or similar metals, on both sides, and a thin conductive wire that will only serve as a fixing, parallel to the coil winding and corresponding to its midpoint when the magnet touches. Since even the 1 mm distance between them is very important, placing any object that I set to 1 cm at best, as I use, and performing the stretching process at this object boundary will greatly reduce our margin of error. The reason why we want to coincide with the middle point is that calculating the location and speed of the magnet based on the middle center of gravity at the point of contact, in case the magnet does not approach exactly parallel, and there may be millimetric shifts from top to bottom, gives more accurate results. With the touching of the magnet, this stretched wire, and we carry out this stretching process by wrapping the other end around the stabilizer wire several times so that it opens when slightly strained. Normally, the corner of the stretched wire where the magnet does not touch will lightly touch this wire and provide current. We place another conductive wire connected to the main circuit with similar materials but stretched perpendicularly, and by moving it back and forth, we can adjust the hardness of contact with the other wire, that is, the duration of the current. Immediately after the magnet touches the stretched wire and a short-term peak occurs, we adjust their positions so that the two wires are separated from each other and the current ends due to this contact. Thus, when the magnet touches the coil winding, even though the stretched wire touches the magnet, it will not be in transmission, and thus we will be able to see the moment of contact more clearly. Here we see the stretched wire that is not connected to the circuit. The other end of the wire can easily go back in the form of a ring. We wrap the near end to us like this and stretch it to the wire. This is connected to the black thick wire coming from the circuit seen at the bottom. We stretch this by wrapping it from top to bottom. And we touch it to the other wire. When the magnet touches the horizontally stretched wire, it moves away from the vertically stretched wire and becomes deactivated. On the contrary, if this current continues during contact, the peak waves formed prevent the moment of contact from being seen clearly. Since the key should not contain any metal that would attract the magnet and should not reduce the forward speed of the magnet, we preferred a design we made instead of the ready-made ones. When we prepared a very thin coil wire connected in series to this second wire that will complete the switch function, we placed it in our large coil winding and tried it on its ends, adjusting it so that it would attract the magnet again when current was applied, just like the big coil winding. After stripping the wire end coming from the mini coil winding and making it conductive, we can connect the end by attaching it to the back or by a similar method. Since this coil winding is very thin and small, it will have almost no effect on the movements of our main coil winding. Thus, the magnet will be placed as a switch 1 centimeter before the main large coil winding. The stretched conductor will touch the middle part of the conductive face of the permanent magnet, and the short circuit will be completed with the wire coming from the mini coil winding of this magnet. When it is not touching, the circuit will be incomplete and open. During the movement of approaching the main coil winding, the switch here is put into conduction by touching the magnet for a while. The peak formed on the wave showing the current, due to the magnet effect on the mini coil winding and the start of the current, and secondly, after a while after this peak, an increase in its amplitude downwards, as I will explain in a moment. We will be able to calculate the moment when the movement stops and the parallel moving starts. That is, the moment of contact. Before moving on to the experiment, in order to carry out the experiment more accurately and standardize it, it is necessary to pay attention to some details, some of which I have decided from the results of my measurements after months of measurements, and some of which are already widely known. In order to make measurements with the least electrical noise values, it is necessary to set the voltage values per unit of the oscilloscope to the lowest value that provide other criteria, so that the voltage waves do not extend beyond the screen and the highest amplitude can be seen. It is necessary to keep the apparatus and oscilloscope in the experiment far as much as possible from the sockets, electrical cables, etc., and to use them in a grounded socket. Again, if possible, a power source that produces less electrical noise should be used to energize the coil winding with an accumulator or battery. It is necessary to keep the experiment stand away from materials such as iron and steel-like materials that can attract magnets or large aluminum and copper that may cause eddy currents during the magnet movement. For the waves that show current, voltage, integral, and energy amount in the oscilloscope, the same value per unit interval should be chosen, or if not, the closest value should be chosen so that the screen image does not overflow, and the starting reference point for the zero value of these waves at the end of the screen should be the same. Otherwise, in voltage, current and power waves and energy calculations, especially during the mathematical multiplication or calculation of the fractions after the decimal point on the oscilloscope, there may be deviations from the real result value, although not enough to change the experimental result. In order to visually and numerically compare the received and given energies in the control experiment, we will conduct before the actual experiment using coil winding or shunt resistors with resistance values that are multiples of the values on the oscilloscope, or at best, exactly the same as the values reduces the margin of error considerably. In addition, in order to reduce the margin of error, it is beneficial to ensure that the coil winding and shunt resistance values are not too small. That's why I set the shunt resistance value as 1 ohm, the same as the coil winding resistance value. Conversely, I could set the resistance values of both to 0.1 ohm. Only then would the precision of our resistance measurements, and therefore our overall measurements, might decrease by almost a factor of 10 times. If we cannot obtain a full 1 ohm resistor and the resistance value is slightly less than 1 ohm, we can create the desired resistance value by soldering a few of the metal sockets or coil wire that we would normally use during the connection at the ends in series without winding it, that is, without turning it into a winding. In order for the magnetic energy generated to be greater and to be observed more clearly, the coil winding and especially the magnet size must be kept within the limits I mentioned, and the magnet in the pendulum must be centered both on the right and left, and with the coil winding at a more or less distance. For this reason, I used a grade N52 neodymium cylinder magnet with dimensions of 70x50 mm. However, of course, a smaller size, different grade, and a magnet with a rectangular or square front face can be used instead of a cylinder. In order to make precise time and speed measurements, the touching surfaces of the permanent magnet and the coil winding must be parallel and perpendicular to the test stand. While the wire acting as the S2 key is stretched, it should also be parallel to them and center the permanent magnet at the moment of contact. In order to avoid errors, it is beneficial to first conduct a control experiment in which we will measure in the same environment and in the same way as our main experiment. The purpose of doing the control experiment is to observe that the energy gained without permanent magnet movement is less than the electrical energy given before the actual experiment, and to see whether the experimental setup and resistance values are correctly. To do this, first of all, we cut the current by turning on the switch and turning off the switch after the contact, in order to approximately find the wave duration that we will include in the measurement in the experiment we will do shortly. And with the method we explained, we found that the time until the magnet touches the coil winding is 114 milliseconds.
In order to determine the time interval that we will make a comparison in a moment, we turned on the switch and closed it when the magnet touched the coil winding, and these waves were formed.
First, I increased the unit time interval of our wave to 5 milliseconds and moved the cursor to the touching point where the waves started to move in parallel. Then, when we set the unit time to 20 milliseconds and moved the cursor to the starting point of the waves, we saw that the total interval was 114 milliseconds. We will use this period from the turning on the switch to the time it touches the magnet coil winding to represent the addition of the same amount of time under the same environmental conditions in the actual experiment we will conduct later. A few milliseconds less or more of this time than in the actual experiment does not affect the measurements or change the oscilloscope values, and you can see the measurements by trying this. Here, if we want, we can use the movement time found in the actual experiment as the time in the control experiment by not making this measurement, which we have already made only for duration, and leaving the control experiment to the end. Now that we have found the time for valuation, we can proceed with the adjustments of our oscilloscope. The settings and circuit connection of the oscilloscope will be exactly the same as in the actual experiment we will do shortly. One of the probes of the oscilloscope, which is blue, is called V on the oscilloscope in terms of voltage signaling to measure the voltage coming to our coil winding, and the other is called A on the oscilloscope in terms of current symbolization in order to measure the current passing through the system with the falling on a 1 ohm resistor. We connect it to the shunt resistor terminals as shown in the circuit shown in the figure. In order to avoid a short circuit, with the circuit connection made in this way, although the voltage wave is actually in the same direction as the wave that will show the current, the reverse direction downside will appear on the oscilloscope, the right side will appear, so invert the voltage probe settings to be able to compare the waves more easily and to make it appear on the screen in an upward direction, as in the yellow current wave. That is, we select the option to reverse the wave. By paying attention to the items I mentioned above in the oscilloscope, we select the suitable voltage, current and amplitude values per unit for mathematical function. I set them all to 2. I chose the time interval per unit as 50 ms per unit interval. In the integral function used to find the energy consumed by the oscilloscope, I chose the wave that would be formed as a result of the fx function as the power wave whose area would be measured by the integral rather than a ready-made wave. In the first step, after selecting the result at times b as the function fx, we select the first channel for fxa and the second channel for fxb. So we multiply current and voltage. The wave that will be formed is the spent electrical power wave, and the measurement of the area under this electrical power wave that occurs in a certain period of time, that is, the integral process, gives us the total electrical energy we consumed. In summary, in this way, we command the oscilloscope to first multiply the current and voltage to create a power wave, but to show the energy spent in this wave according to time with a purple wave without showing me the resulting wave. Now let's start measuring. First, we put the oscilloscope in single scanning mode. Again, in order to create similar environmental conditions as in the actual experiment, we fix the permanent magnet at a distance of half of our total distance of 5 cm, that is 2.5 cm, in the middle, so that it does not move at all when current is applied, because even a few millimeters of movement can cause incorrect measurement values due to the formation of opposite labor. In order to fix it in an easy way, I will put a piece of plastic at least 2.5 cm in between and start and end the current while squeezing the magnet between the coil windings. Thus, we will have created, on average, the same distance from the coil winding and the same interaction environment as in the original experiment. Although, as far as I can see from comparative measurements, the position of the magnet or even its presence in the environment does not cause any observable change. However, we still found it useful to make comparisons in this way in order to ensure the same environmental conditions. We turned the switch on and off for a period of time that would not be much different from the permanent magnet movement time in the actual experiment we will do shortly. Waves appeared on the oscilloscope screen after the moment of contact.
For the control experiment, we put a piece of plastic in 2.5 cm turbidity between them and tighten it very much to prevent the magnet from moving. And then we turn the switch on and off.
First of all, since our shunt resistance and our main coil winding resistance both have a voltage, their general value should be equal except for the beginning and end parts. In other words, the blue wave showing the voltage and the yellow wave showing the current should be on top of each other and parallel, except for the beginning and the end. It is also worth noting that the coil winding and shunt resistance values may not show exactly 1 ohm or 1000 milliohms during measurement, but may show resistance value errors in several milliohms. Again, electricity in the environment, noise and heat resistance differences caused by current can be reflected on the coil winding and the current resistance in a way that creates different amplitude changes. The fact that the blue wave amplitude, which is proportional to the energy spent in the coil winding, is slightly higher in some parts than the yellow wave amplitude, which is proportional to the heat energy released in the coil, will show the magnetic energy gained against us as less. However, small differences here will not change the experimental result. The most important point to know here is that its opposite, that is, the wave amplitude showing the current shown with the yellow wave, or the coil heat energy created by taking it opposite this amplitude, should not be more than the wave amplitude showing the voltage with the main wave and the electrical energy consumed. If it is wrongly too much, it should be increased by increasing the number of turns in the coil, winding by calculations, or, if necessary, by trial and error, or by connecting materials that may experience additional resistance to the coil winding ends in series, thus increasing the voltage falling on the coil winding, and therefore its width, so that the energy spent in the coil winding is not less than the coil heat energy gained, as it should be. If we do not have a milliohmmeter when adjusting the coil winding amount, here is the blue voltage wave on the coil winding with an amplitude proportional to the amount of resistance, with the yellow wave showing the shunt resistance with a resistance of 1 to 10, and the yellow wave showing the beginning and end with the same amplitude, that is, exactly overlapping and parallel, shown to be. If we wind by trial and error, we can set the coil winding resistance to be equal to the shunt resistance, that is 1 ohm, with the help of an oscilloscope. Now let's look at the electrical energy consumed in the oscilloscope we have adjusted. Here, after selecting the beginning of the integral calculation, that is the beginning of the wave, with the cursor on the oscilloscope, we bring our cursor to 114 milliseconds, which is the time we have just found as the end time point in order to have the just same conditions in our actual experiment, and we select the same cursor mathematically and select the topmost point of the purple wave, which shows the integral result. We put it at the end point. We found that we spent 3.96 joules of electrical energy this way.
In the control experiment, we again placed the 0 reference points for current, voltage, and integral at the top. We chose the value 2 as the unit for all. As can be seen, the resulting current and voltage waves are above and parallel. Now we have selected and initialized the mathematical integral function. We chose f2 as the source. We limited the measurement to 114 milliseconds after the start of the integration function and the time we found, and moved the cursor to this point. We chose A times B as the FXA operation, channel 1 as FXA and channel 2 as FXB. In this selection, we find the value 3.96.
Now let's move on to the second mathematical operation on the same waves to find the gained energy or the heat energy released. The only difference in this calculation is to change FXB to the first channel so that the current wave multiplies with the current wave and not with the voltage. The positions of the cursors where we select the starting and ending point of measurement of the wave and all other settings are the same. The reason we do this is that we use the formula I squared times R times T to find out how much energy we gain against the energy consumed, and first of all, the coil heat losses. If we expand the formula a little here, it equals I squared times R times T. It is the current multiplied by the result of the ohmic resistance multiplied by the current times the time. It is also equal to current times the static current state and the falling voltage on the coil wire under the pure ohmic resistance state times time. Static refers to times of constant generality that have reached equilibrium except for the beginning and termination moments of the direct current, where the current does not change its intensity and direction. Since we set the pure ohmic resistance value of our coil winding as R is equal to 1, and multiplying the current by 1 in the formula does not change the result, when we multiply the current wave with the current wave on the oscilloscope, what we actually need is the current wave, and the voltage falling on the coil ends in the static state when the winding is not made or when the current does not change anymore. By multiplying the wave, we find the power wave consumed for heat. Of course, since the coil wire in our experiment is wound, in addition to the plain winding state, electromagnetic interactions and losses also occur due to dynamic changes such as the starting and ending moments of the current, and as in our experiment, the total voltage falling on the coil winding ends is greater than this pure ohmic resistance voltage value. However, the amount of power and energy spent for heat loss is calculated as we have shown for these times and does not change. In this way, we find the electrical energy consumed for heat in the coil winding by using the mathematical integration process in the oscilloscope in this power wave that occurs against time. Yes, with these settings, we found the energy spent for coil heat losses to be 3.96. Afterwards, when I selected channel 1 instead of channel 2 as the FXB, the value of 3.96 did not change. Here, the energy spent for heat is also the heat energy gained, and this should not be higher than the energy consumed for the coil winding, which was the main reason why we did the control experiment. Yes, as can be seen, the energy spent behind the coil heat is not less than the heat energy of the winding coil as desired. It looks equal. In fact, we should have found the coil heat energy to be less than the energy consumed, even if the small amount of additional electromagnetic losses occurring, especially during switching, were less than they were.
However, the difference was not reflected numerically in the calculations because it was even less than the next scale increment value in the integral mathematical process we used in the energy calculation of our oscilloscope.
By trying the increases and decreases, we saw that the mathematical minimum integral increase value was 0.08 unit or 0.08 joules for our experiment after the values we selected on our oscilloscope, depending on the values we chose per science interval, and therefore a difference below this value is not reflected in the result. If such a difference were found, the result would not change except that the calculations would take a little longer. In our actual experiment, we would have started from minus with a loss equal to this value. However, we would add this value as the observed and gained electromagnetic losses to the total amount of gained energy in our actual experiment, and therefore the result would still not change. Thus, we saw that our experimental setup worked correctly, or that there was no error that would change the result. And now we can move on to our main experiment, where we will measure energy in the same way. Now let's move on to our actual experiment. Since the environment in the control experiment should not change, we try not to change the location of the stand. We did exactly the same as in the first control experiment measurement. Now we start the current by pressing our main switch, S1. As the magnet rapidly approaches the coil winding, the front face of the magnet and the stretched wire in the roll of switch S2 will first come into contact with the front face of the magnet 1 centimeter away, completing its short circuit, and a peak wave will occur with the activation of the inner mini additional coil winding. When the magnet moves a little further, the two wires will be disconnected and the mini coil will be deactivated, and thus the moment of contact can be observed more clearly. Yes, when I turned on the switch S1 and then turned off it, current and voltage waves occurred as follows. We put our oscilloscope into single scan mode. We quickly opened the switch and closed it when the magnet touched the coil, winding, and waves were formed like this. As can be seen, due to the opposing force created by the magnet on the coil winding, which increases especially as the magnet approaches the coil winding, the current wave is in the downward direction and the voltage wave is in the upward direction. Let's make the mathematical calculations in order that we made exactly the same as what I explained in the first control experiment measurement above. With such calculations, we find that the electrical energy spent for the coil winding is 4.18 joules, and the energy spent for coil heat losses without changing the starting and ending points of the cursor is 3.58 joules. First, we started the integral operation. We opened our cursor. We reduced the unit duration of the wave and determined the beginning and ending location from the integral mathematical function. After moving the cursor to the touch point, we selected the math part, that is, the integral result, as the unit to be measured with the cursor. By multiplying channel 1 and channel 2 with these adjustments, we found the value of 4.18 joules. So our total spent energy is 4.18 joules. When we multiply channel 1 and channel 1 again, we found the value 3.58. So we found the value of 3.58 for coil heat losses. Now let's calculate the final speed and kinetic energy of the permanent magnet when it touches to the coil winding. First, we'll take a closer look at the yellow wave we used to measure current. So why did we use the wave that shows current and not voltage? Because artifacts occur less on this wave and there is no time delay. For this reason, we can observe the resulting epic wave and the moment of contact more clearly and accurately. As can be seen, we see an upward peak or group of waves to the left of the wave that disrupts the normal slope. After the magnet of the wire that acts as the switch of this wave group, sometimes due to the negativities on it and the lack of conduction in the switch, it can sometimes cause time gaps to be seen, decreasing to the normal reference wave level, where there is no current in the mini-coil. This peak wave starting point shows the distance 1 cm from the permanent magnet to our main coil winding. As we can see more clearly in the wave showing the current, the first moment when the wave starts to move parallel while it is traveling downwards shows the moment when the magnet touches the coil. Now, in order to measure even more precise time, we adjust the time as 2 millisecond unit intervals. With the cursor, I measure the time between the beginning of the peak and the moment of contact as 9.64 milliseconds. Now let's determine the times to find the final speed. For this, we set the unit interval to 2 milliseconds. We move the cursor to the beginning of the first peak wave and the cursor B to the first contact point where the waves start to run parallel. With these adjustments, we found that the time difference between the two cursors was 9.64 milliseconds. Therefore, when approaching this example of a permanent magnet, we calculated that it takes 9.64 meters to travel 1 centimeter. Therefore, the average speed of the permanent magnet in this range is 1.03 meters when we divide the distance taken by the V sharp X T formula, that is, 1 centimeter by this time. We can see what has been said again on the speed-time position graph. As can be seen from the graph, of course, the final speed at the touching moment, and which we need to use in the main calculations, will be a little more than the average speed in the interval starting with 1 centimeter left. However, when we can show that we have gained enough magnetic energy to present the proof, even at the lower speed we use in the calculations, we further reduce our margin of error. In order to find the gained kinetic energy from the 12mv² formula, when we measure the mass of the magnet with a digital precision scale, we find the value of 1.44 kilos. Substituting it into the formula, it equals 1.2 times 1.44 times 1.03 squared. To find the potential energy gained by the magnet as it rises upward due to the movement of the pendulum, we use the formula m times g times h, that is, mass times gravitational acceleration 9.81 times the height. Here, when we measure the height of the magnet in the initial position with ruler and the value at the height adjacent to the coil winding after turning on the switch and applying electricity, we find that the difference between them, that is, the amount of rise, is 20 minus 14 equals to 6 millimeters. When we substituted the values in Formula D, we found the following value: 1.44 kilograms times 9.81 times 0.06 meters equals 0.08. Now let's find our total winning energy. This is the energy gained due to heat loss plus, when we replace the additional detectable electromagnetic losses plus the kinetic energy gained by the magnet plus the potential energy gained by the magnet, the total gained energy is 3.58. On the other hand, the electrical energy we spent in the coil winding was 4.18 joules. When we subtracted the total energy gained from this value, we saw the existence of an energy that seemed to be 4.42, 4.18, that is 0.24 joules more, as if shown in a tabular form through this experiment. Considering losses such as friction, the additional energy gained will actually strengthen the proof. We did not include these details in our experiment in order to avoid dealing with the complexity. The only source of the additional magnetic energy released, which appears to be much more as we have shown here and previously in the videos in our electric motor with a different design, is the pathways that provide the magnetic attraction force in the permanent magnet. It can be concluded that as much energy as the additional magnetic energy that seems to be transferred to the outside is lost in the internal pathways of the magnets that provide magnetic energy during movement. Finding out how this energy loss occurs will be the subject of further research. However, if we need to establish an example hypothesis so that it can be shaped in our minds, for example, the dynamic changes that occur with the movement towards the coil winding, the magnetic waves that naturally occur with the spin and orbital rotation of the electrons in the permanent magnet atoms, and in a sense, a slight opposing force on the routine rotation directions of the electrons at the other end of the waves. As a result of the combination, a very small part of the angular rotation speed and kinetic energy of the electrons may be lost without damaging the magnet material structure. In other words, it is not an energy whose source is unknown, but a limited and shape-changing energy. You can see the experiment details, the link and contact information of the article I wrote on this subject in the comments. I invite everyone to work together to repeat the experiments together and take the electric motor and other studies to the next level.